All right, so we are recording. The audio and the video should be coming through, as well as the slides. So let's get started. Just before class, there was a question about problems on the exam, and I thought I would go ahead and mention that just so it's on the recording. First off, our exam isn't going to be for a little while, our first one, because we're going to include reactions, trusses, and then our next topic, which is shear and moment diagrams. But one thing I'll say about it is I tend to not, what's the best way to say it? I tend to not micromanage a lot on the exams, especially when we get into upper classes. Usually what will happen is I'll say something like, here's the problem, and then, you just do it. And I let you sort of figure out, how you want to solve the problem instead of saying, you must do it one way or must do it the other. The idea, like my thought is, this class is all about providing you tools, to tackle a problem. And then the test might be something like build a shelf. You use, whatever tools you want to build the shelf, But we'll talk about the exam specifics as we get closer. It's not going to be for a few weeks. I know my folks in statics, they have an exam coming up next week. But I keep using this word exam. We don't have exams in college. We have celebrations of learning. All right, let's get right into it. Well, first off, before we get into the announcements, it was nice to see some of you yesterday in the lab, and I think that there might be a couple of you that I'll see later this afternoon. I had told some of them in the lab that I would have come up with some jokes, but I didn't think of it in advance. I didn't have the foresight to come up with those in advance. Foresight, yeah, okay, all right. I'll move on. So in terms of the schedule, homework 3.2 has been graded. The solution's available. You all have homework 3.3 due today. I wanted to be clear on that homework assignment. I only was really interested in you solving that. There you go. I'm glad somebody got it. Yeah, that was a land surveying joke. For homework 3.3, I was only interested in you solving those two joints. You didn't have to solve the entire truss, and I'm okay if you did, but that was all I was interested in. And the reason I mentioned that is the next homework assignment, the one that I'm assigning today, involves the method of sections, and I'm only interested in you solving the members indicated. You don't have to solve the entire truss, just the ones that are indicated in the problem. And I wanted to say that now, in case I forget as we move into the lecture. Any questions before we chug along? All right. So we have today our last lecture on plane truss analysis. Now, I'll go ahead and tell you that this is not the last time that we're going to analyze trusses in this class, because later on when we start looking at, let's say, truss deflection, we're going to have to go back and analyze trusses again. And when we look at truss influence lines, we're going to have to analyze trusses again. But after today, we're going to move on into one of the I don't want to say the most important topics of the semester, because I think that everything that we're doing in here is pretty important. But shear and moment diagrams are a pretty seminal topic in structural analysis, and so we're going to spend a fair amount of time on that. In terms of lectures dedicated just to trusses and to truss analysis, this is it, because we've done 3 on the method of joints, but today we need to discuss the method of sections. I say we'll explore this one later. I copy and pasted this slide from a previous lecture. I should probably update that to say we'll explore this one today, because this is what we're doing, is the method of sections. So let's talk about the method of sections. We've sort of hemmed and hawed around it, but now it's time we actually, go through it. Let's talk about this. The first thing I'll say about the method of sections is I think that the method of sections is one of the most valuable kits or tools in your toolkit for the FE exam. Because what will happen on the FE exam, a very common problem is, let's take this truss that you have here on the screen. You'll have a problem that'll say something like, here's the truss and it's got all these loads on it. What is the force in member, I don't know, IJ? And you can handle that one of two ways. Start doing method of joints analysis, which is fine. There's nothing wrong with that, but it can take a while because, if you're trying to do member IJ, you might say, okay, I'll start at joint L, and then I'll go to joint K, and then maybe joint E, and then joint J. So you're having to do quite a bit of work just to get to IJ. Whereas if you just cut a section in some moments, at a particular point, you could be done with it. So it's a very valuable toolkit for the method or for the FE exam. But in general, I don't want to teach to a test. Like, I don't want to teach the class just so you pass the FE exam. I want you to understand, holistically what's going on. The method of joints is really great if you want to analyze the entire truss. I find that the method of joints is easier, it's quicker, it's less prone to errors, and it's less elaborate. And a lot of times, and more often than not, as structural engineers, we end up needing to solve the whole truss than we need to look at a particular member. But if you do need to look at a particular member instead of the entire truss, then the method of sections is more appropriate. So it's great for spot checking your results. It's great for verifying designs. Like if you're a structural engineer and you're working on a project and you look at the truss and you go, that one member looks a little small. It doesn't look like it's big enough to carry the load. Well, then just cut a section to determine the force in that member and then assess your design. Now, there's a couple things going on with method of sections that makes it a little different. First off, when we're dealing with the method of sections, we're dealing with what are called non-concurrent force systems. So if you go back to statics land, method of joints is basically what you do in the first part of statics. It's a particle statics problem, the statics of particles, because all the forces all meet at a single point. We call that a concurrent force system because all the forces all meet at a common point. So when you're doing a method of joints analysis, you only have two equations of equilibrium at your disposal when you're looking at each joint. That's the sum of forces in the x direction and the sum of forces in the y direction. There's no moment, okay? But when you're doing a method of sections, you have that third equation of equilibrium because it's a non-concurrent force system. The forces don't meet at a common point. If you cut a section, here you can see on the slide, this is section 1-1. And they cut a section and they look to the left, you can see that there's forces going all over the place. They don't meet at a common point. So you have three equations of equilibrium. You can utilize that sum of moments expression. Now, when you're using the method of sections, you have a similar limit. So when you did method of joints, remember, when you start planning out your method of joints analysis, you can only analyze a joint that has at most two unknowns because you only have two equations of equilibrium. So with the method of sections, you can only analyze the section cut where there are at most three unknown forces. So if you see this section 1-1, it cuts through three members, okay? And you can only cut through three unknown members because you have three equations. Now you could cut through more than three. You could cut through 4 or 5 or 6, what have you, as long as you already knew the internal forces in those other members. Again, three unknowns, that's your limit. Now, the other point I'll mention is a point on strategy. It really doesn't matter which direction you look. Like, you can cut a section and look to the left, you can cut a section and look to the right, it doesn't matter. On this particular truss, they cut a section and you can see they look to the left. I think it's usually advantageous to look towards the side with, the way I put it on the slide is the side with less going on. Like if you cut a section and look to the right, there's more truss, there's probably more loads, more expressions. Like you'll get the same answer whether or not you look to the left or look to the right, but just based on the structure, it just seems easier to look to the left because there's just less stuff going on the left side. So I always tend to advocate to make it easier on yourself. You're going to have less errors, you're going to have less hiccups, and ultimately I think you'll arrive at the same answer with less work, and I'm up for that. Okay, so we have a pretty intense looking truss here. What we're going to do is we're going to solve for members CD, CK, and JK. So let me see if I can try my pencil. Forgive me if this doesn't come out perfectly straight. That's the thing. You can't use your pen on Blackboard Collaborate. You have to use your mouse, or at least I haven't figured out how to use my my pen. Okay, so we're trying to solve for these three members. So I think it is pretty safe bet that we're going to cut a section, that way through the vertical component of the truss. Now, whether or not we cut a section and look to the left or the right, again, ultimately, it doesn't matter, okay? But what I'm going to do is this. I'm looking at this truss and I see, just based off of symmetry, it just seems like there's less going on the left side of the truss than there is the right side of the truss. Just less members. I think I'm going to have to draw this as a sketch, and it just seems like I'd have to draw less if I look to the left. Maybe that's me being lazy, but again, it probably doesn't matter all that much, but I'm going to flip a coin and go with it. I'm going to cut a section and look to the left. Okay, let me stop my share. And let me go back and share the screen. Okay, so here's the slide, or did somebody say something? I thought I heard a cue or something from Blackboard. Oh. If y'all, that was an accidental hand raise. Oh, okay, no big deal. Let me get this charger plugged in. I got too many cords over here. Okay, here we go. All right, so let me make this. Let me see if there's a question. Right. If there was an X component for the reaction force at A, would it be more judicious to choose the right side for analysis? That's a good question, and they're probably, if we're being strict about it, there might be an argument to be made to cut a section and look to the right, because you've got, two loads in a reaction to the left, two loads in a reaction to the right. That might be the what swings your vote. However, as you're going to see with what we do with this particular section, you're going to see that for this particular truss and this particular problem, that probably wouldn't play into it. But we'll see that as we progress. Okay, so I'm going to address that question of yours again a little bit later. Okay, so we're going to cut a section here. We'll call it section 1-1, and we're going to cut through those three members. Now, like I said, I'm going to cut a section and look to the left. If I'm being honest, one of the other reasons I've always preferred method of joints over method of sections is, in order to do this properly, I've now got to redraw the truss all over again, or at least that left portion. So we'll say cutting a section. And looking left. So now I'm going to try and draw this all over again. Actually, let me do something real quick. Oh. Hold on. There we go. I was trying to get my... Sometimes the scroll bar doesn't quite want to show up, so I have to trick OneNote to doing that. Okay. All right. So again, one of the things I've never really been the biggest fan of, the fact now I have to redraw this all over again. So I'm going to draw everything to the left of that section. So forgive my artwork. I'm going to do the best I can, and you all can sort of go along with me. I'm actually going to try and put this in the middle. So we have this, have this, and that, and then that. That's all good. Okay, so we've got this member, this member, this member, that member, that. I will say, this is one of those places where having oh, go away. It's one of those places where having graph paper or something like that helps, because you can draw this out a little bit more neatly. Also, having your self a straight edge helps. Okay. Now, the way I'm going to draw everything past this is I'm going to have, here's my member, but then I'm going to have these sort of dashed lines to indicate, well, here's where the member would be. and then sort of goes up like that. Here's where the member would be. Just for sake of discussion. Okay. Now let's start labeling these. So this was point A, this was joint I, this was joint J, and then off out here that was joint K. This is joint B, this is joint C. See if I can darken that up a bit. Those are the three members I'm solving for, and this is joint D. Okay. We have loads. This is 20 kips. This is also 20 kips. And then this has a reaction of 45 kips. And then let's go ahead and put our dimensions. 30 feet, 30 feet, 30 feet. Do better than that. Okay. And then we have this dimension here. That dimension's also 30 feet. And then we got a few dimensions over here on the left, so here I can maybe do a little bit better. Line that up. This is 5 feet, 10 feet, and that's 15 feet. Okay, and maybe because there's a lot going on, maybe I'll try and darken these truss members in a bit so you can kind of tell, like, okay, that is the truss. Oh, that's horrible. Maybe I'll do that. That's a little better. Yeah, that, again, like with method of sections, you do so much drawing, it's like, goodness, I'd like to just start doing the problem. Okay. Now, let's go ahead and start attacking our unknowns. Now, when I start drawing out these unknowns, just to make things simpler, I usually always assume, I'll say all unknowns assumed in tension. And let me say this, that probably isn't as absolutely necessary. Hold on, let me get to your question here a second. That probably isn't as necessary, the assuming intention for this problem, because usually by this point you could probably look at these trusses and kind of figure out which members are in tension and which members are in compression, but I'm just going to do that for the sake of consistency. Now, question is, were we not required to draw the trusses on previous homework assignments where we did method? Well, yeah, but that's the point. It's like, you know, you draw it for the initial problem, but then you have to draw it again where you're cutting a section. I guess you don't necessarily have to redraw it, but I've always felt that in order to do a method of sections correctly and try and reduce the amount of errors, you end up like redrawing it ends up being a good practice to enact. So it just ends to be a bit more work intensive for your pencil. So yeah, and yeah, if y'all have any questions, please, you know, throw them out. Okay, all right, so let's start drawing out our unknowns. This is CKY, this is CKX, and remember this member is at a 1-to-1 because it's 30 foot over and 30 foot up. Sorry about that. This member here, let's call this PD. And then this member here, we'll call this JKX and JKY. Okay. And then this member is actually at a 1 to 6 or 6 to 1 because it's 30 foot over and it's 5 foot up. So yeah. Okay, I'm going to give everybody a sec to catch up on that, and then we'll talk strategy. Okay. Hopefully you all are caught up, and if you need any time or whatnot, just let me know. Okay, so we have 3 unknowns ultimately. So we have unknowns member CD, member CK, and member JK, okay, through this section. Now, we have 3 equations of equilibrium, sum of forces in the x direction, sum of forces in the y direction, sum of moments. So let's talk strategy. First off, if we summed forces in the x direction, we'd have 3 unknown components. And if we sum forces in the y direction, we'd have 2 unknown components, right? In the x direction, we got CD, we got CKX, and we got JKX. And in the y direction, we have CKY and we have JKY, okay? So right off the bat, I think it just makes sense that if we're going to use an equation of equilibrium first, we ought to sum moments first, okay? That just makes sense from a strategy standpoint. Now, where do we sum moments? About which point? Well, remember, when you sum moments, you're trying to sum moments in such a fashion that you eliminate as many unknowns as you can. And so the idea is if you can find a point where 2 of those unknowns intersect, you can sum moments there to solve for the other unknown. So I propose that there are 3, I'll say, optimal locations about which to sum moments. Okay, let me scroll down a bit so I'm not squunching this down. Okay, so let's talk about option 1. Option 1 would be joint C. Okay, because if I look at joint C, I have member CK and member CD all meeting at joint C. So when I sum moments at joint C, I don't have to deal with those, and I would only solve for member JK. Okay, so that would be one place to sum moments. Another potential place to sum moments would be joint K. Joint K. Now, here's the thing. Of the 3 locations I am going to point out, this one is not recommended. Now, here, let me ask you this. I'm just going to ask the class, okay? You could sum moments at K to get one of your unknowns, but I'm not recommending that you sum moments at K. Can anybody guess why I'm not recommending that you sum moments at K? It will only solve for CD. You're right. If I sum moments at K, that will isolate CD. And what's the problem with what does that leave me with? That leaves me with 2 diagonals. Exactly right. That leaves me with 2 equations, 2 unknowns. So while I can sum moments at joint K, it's not recommended. Okay. So summing moments at joint K, it'll work, but you'll end up having to do more work in the end. The third option is, I'll call it point, I don't know, O or point X, whatever you want to call it. Think about what's going on. Okay, joint C eliminates C. So look at it this way. This eliminates CD and CK. This eliminates, what is it? C, I don't need another parentheses there. CK and JK. So think, this one eliminates CD and CK. This one eliminates CK and JK. So I guess this one's supposed to eliminate, what is it, CD and JK? Well, how do I do that? How in the heck do I eliminate those two forces? Well, it's easy. I find the point where they intersect, which is like all, if you track it out, it's like all the way back here. So we'll say this right here is point O. And so if you do some moments there, you would eliminate CD and you'd eliminate JK and you solve for CK. And honestly, that's a reasonable choice. There's nothing that says you have to sum moments on the truss. You could sum moments anywhere. That's a particular option as well. So between the two options that are recommended, I would recommend that you sum moments about either joint C or point O. I'm going to pick joint C simply because all the dimensions are right here. I don't need to like feet to get point O. And so you ought to try it out and see if it works. But this is the one that I'm going to use. I'm going to use point C. All right, so let me actually do that right here. I'm going to sum moments about point C. Now, before I do that, I do want to remind everybody of one principle from statics. And I'm actually going to stop the share for this because I want to, I don't want to clutter up my my screen here, and I want to kind of use my board. I want to remind everybody about the principle of transmissibility. So the principle of transmissibility states that if I have a force that acts along, let's say, some given line, and remember, forces are represented by vectors, right? Vectors are objects that just they're mathematical objects that have a magnitude and direction, right? So I can take that object. The principle of transmissibility states that I can take that object and I can move it anywhere along that line. Remember, we have a name for that line. We call it the line of action. Well, the point I'm making is that you can do the same thing with the X and Y components. So let's say here's the same line of action, right? And we have the X and Y components. So this is Fy and this is Fx. We can take those X and Y components and we can slide them up and down that line, and they would be statically equivalent. We can move it here, we can move it here, we can move it back here. It doesn't matter, okay? The point I'm making is that when you go to your method of sections analysis, I'm going to take one of those members and sort of move it to a point that's somewhat advantageous, and you'll see what I'm going to do. All right, so okay. So we're going to sum moments about point C, and let's just start tackling each of these one at a time. So we'll start at the left and we'll work all the way over. So starting at the left, we have 5 kips times a moment arm of 60 feet, okay? And that's going to be on the left side of the equation. So this is 45 kips times 60 feet, okay? So we've got that. We've got the 20 kips times a moment arm of 30 feet. So that's at, so the first one's at joint A, the second one's going to be at joint B. Now there's a load at joint C, but we can ignore that. We don't have to worry about it, okay? Because we're summing moments at C. We also do not have to worry about CD, we don't have to worry about CKY, and we don't have to worry about CKX. So the only thing we have to worry about is this JK component. So we've got these X and Y components, this JK, JKY and JKX, and I can move those along that diagonal path, anywhere along that line of action. And what I'm going to do is I'm going to take those forces. So maybe I'll put it over here. So this is J, this is K, and I've got that X and Y component. I'm going to move that X and Y component right at J. So this would be JKX, JKY. And the reason I'm doing that is because if you move those X and Y components over to J, what happens to the Y component? It goes right through C. And so I don't have to consider the Y component. All I have to do is consider the X component, and I have JKX times a moment arm of 25 feet. Okay? And the way I've got that drawn, that's going to be on the left-hand side. So JKX 25 feet. All right. Now, I want to take a sec and make sure that everybody is comfortable with that. I don't want to just do that without exploring any questions that you all might have. Does anybody have any questions about that before we move on? Okay, good. All right. So I have JKX times 25 plus, what is that, 45 times 60? 45 times 60 is 2,700. And that's foot kips equals 20 times 30, which is 600 foot kips. So if I have JKX, I'm solving for JKX, what do? I take the 2,700, I move it on over to the other side, I take that and divide it by 25, and that's going to give me JKX is a negative value, and that's 84 kips, or in this case, 84 kips. It's negative. I had it pointing to the right. That was wrong. It's pointing to the left. Again, if that's too quick, if there's too much going on, you let me know. We'll take our time with it. Okay. All right. Now let's go back to our diagram. First off, whenever you have a diagonal component, one of the diagonal components, immediately solve for the other. It doesn't matter if it's method of joints, method of sections. When you have one, solve for the other. So I have JKX. I'm going to go ahead and solve for JKY. Now JK is on a 6-to-1 slope ratio. Okay, so we'll put this down here and we'll say slope ratio. So JKX is to 6 as JKY is to 1. So JKY is going to be 1/6 of JKX. JKY is going to be 84 divided by 6, and it's 14 kips. Now, 14 kips, let's talk about the direction. Up here, we have JK acting upwards. But remember, we got negative for JKX. So this is wrong, too. So JKY is pointing downwards. All right. And so maybe I ought to, box in the answers that we know. Ooh, that's horrible. I can do better than that. Know that. I know that. Okay. Any questions? I can erase this. All right. I apologize in advance. I might be scrolling up and down a bit, so just bear with me. So let's go back up to our diagram. So here's our diagram. And what do we have? So we know, the JKY and JKX. We know those. Okay, so what do we have left that's unknown? We have CKY, CKX, and CD. So we have 2 unknowns in the horizontal, 1 unknown in the vertical. Seems to me that it would make sense to do our sum of forces in the Y direction first. So let's sum forces in the Y direction. Okay. So let's see. What do I have? Well, let's see if I can go off memory. Okay. I know that I had my 45 kip reaction going upward, and I had two 20 kip loads going downward. So 45 kips going up, and then I have two 20 kip loads going downwards. Okay. Now I also have JKY, and I've already figured out that it's going downwards. So I could say JKY is 14 kips this way. Okay, because I know that's going downwards. The only thing left is my unknown in the vertical. I can't remember what direction did I have that drawn. I had that drawn going upward. That's the CKY right there going upwards. So CKY was going upwards. Okay, so I have CKY plus 45 kips is what? 20 and 20 is 40. 40 and 14 is 54. So CKY is positive. 54 minus 45, that's 9. So 9 kips, and that's going upwards because I said it was going upwards, and it's a positive answer. So if I've got CKY, I can use my slope ratio to get CKX. So CKX over some number is CKY over some number. What was CK? What was that? That's a 1-to-1. So 1-to-1. So CKX is going to be 9 kips, and that's going to be going to the right. Okay, so that one's easy. And then lastly, we have our sum of forces in the x direction. All right. This one's going to take a little bit of scrolling, so bear with me. So, how many forces do we have in the x direction total? Well, we've only got 3. We've got CD, we've got CKX, and we got JKX. Now, JKX, we ended up finding was going to the left. You can see that on the bottom right. We got JKX is 84 kips to the left. We got CKX was 9 kips to the right, and we don't know what CD is, but we have CD drawn to the right. So maybe we should write it like this. JKX is 84 kips. CK is 9 kips, and this is CD. So 84 kips is CD plus 9 kips. And so looks like we assumed the correct direction. So therefore, CD is, was that positive 75? Okay. So let's summarize some stuff because I'm getting sick of scrolling, scrolling back and forth. So I'm going to use my little cheat sheet here. So summary. Let's just rewrite all the 5 forces that we figured out. We got CD is 5 kips to the right. We got CKX was 9 kips to the right, and we got CKY is 9 kips upwards. We got JKX and JKY. What do we have? We had this was, oh goodness, this one was 14 kips down. This is 84 kips that way. Go ahead and break out the Pythagorean theorem on these. So CK is the square root of CKX squared plus CKY squared. And I think at this point, like, this should be pretty rote. I mean, the Pythagorean theorem, I mean, we've been doing this quite a bit. All right, so this is 12.73 kips. And then jk is jkx squared plus jky squared. So this is and this is 85.16 kips. And then in terms of your signs, remember, we assumed everything was in tension, and that makes the end part that much easier. We know that CD, when we did CD was positive, so that's 75 kips in tension. CK, when we did CK, came out positive, so that is 12.73 kips also in tension. But the JK came out negative, so that was JK is 85.16 kips in compression. And that's it. I know that was probably a bit convoluted just with scrolling up and down on the screen, but by and large, I got to believe that was a pretty straightforward process. Let me take a second and see if you all have any questions. And give you all a sec to copy this down. All right, before we end, I want to mention something about our next topic. So this is it for trusses, and this is it for trusses on exam one. We have, other than the classification stuff at the beginning, the real meaty topics on the first exam are the support reactions, the truss analysis, and then our next topic, which is shear and moment diagrams. I'll go ahead and tell you that a very, very small amount of calculus will show up in our next topic. Not really. So first off, it's not going to be anything that's incredibly rigorous. If you could take the derivative of x squared, then you're good. Mostly the calculus that we're about to use is going to be used as a check to make sure that what we're doing is correct. We're not going to necessarily need to employ it to solve the problem. So it'll still be very, very algebra and graphical based. I will go ahead and tell you that our next topic is going to require a lot of drawing and a lot of figures. So it's probably not a bad idea. Excuse me. Man, coffee grounds. Excuse me. It's probably not a bad idea to have a straight edge, like a ruler or your student ID, something with a straight edge, because you're going to be drawing a lot of figures. That's probably not a bad idea to have with you. We are also at some point during the topic going to use Excel, and so I'll break out Excel to plot shear and moment diagrams. So I just wanted to, give you a heads up for some stuff that's going to show up. We are going to, like I said, so we are going to have a small amount of calculus show up, and we are going to use Excel. The only other thing I would make sure that you have kind of an understanding of is, and we'll talk about this as we go into it, but just kind of how derivatives work in terms of graphs. Like, for example, if you have the graph of a parabola or a quadratic, and you take the derivative of that, you're going to get a straight line, because like the derivative of x squared is 2x. And so that pattern of going from a parabola to a straight line, and then take the derivative of that, it's a constant, take the derivative of that, it's 0, stuff like that. That actually, if you have a kind of an understanding of that, it's going to make the shear and moment diagram stuff all that easier, because we're going to try and make it as absolutely simple as possible, but those little tricks of the trade will make your life a lot easier. That's actually all I have. We're going to end a few minutes early. You'll have a homework assignment on sections. Again, just worry about the sections that are identified in the problem. Don't worry about solving for the entire truss. The homework is on the method of sections. If you can do those problems or those members, I'm happy. And that's all I have. So I will see you on Friday, and we'll start sharing moment diagrams. That's all I got. Let me turn off the recording, and we'll see you all. And I guess maybe a couple of you will see at 3:30. So.